For nearly 40 years, a single spacecraft's brief flyby of a distant, tilted-over ice giant left planetary scientists with a number they couldn't explain. In January 1986, NASA's Voyager 2 swept past Uranus and recorded electron radiation belts so intense that, by every model available at the time, the planet shouldn't have been able to sustain anything close to that level. Every comparison researchers ran against every other planet in the solar system said the same thing. This doesn't add up. That number sat there, unresolved, for close to 4 decades. Voyager 2 flew past once, took its measurements, and kept going, out toward Neptune and then out of the solar system entirely, never able to return and check its own work. And for most of that time, the honest answer to why was Uranus's radiation so extreme was simply nobody knew. In February of this year, a team at the Southwest Research Institute published what looks like a real answer, not a guess dressed up as a finding. An actual explanation built by comparing that old Voyager 2 data against decades of newer measurements taken much closer to home at Earth. And if they're right, it means humanity's only close look at Uranus may have caught the planet in the middle of an extremely rare cosmic event, meaning almost everything scientists have assumed about normal Uranus for the last 40 years might have been based on anything but a normal day. This is a story about how a decades-old dataset from a spacecraft that's long since left the solar system's outer reaches behind can still produce a genuinely new discovery. Not because anyone went looking for something new, but because the rest of science finally caught up enough to understand what had been sitting in the archive the whole time. To really appreciate how singular this data is, it helps to know that Voyager 2 wasn't actually guaranteed to ever visit Uranus in the first place. Its core, funded mission was Jupiter and Saturn, the same primary targets as its twin, Voyager 1. Extending the journey onward to Uranus and Neptune depended entirely on a much rarer piece of celestial timing. Once every 175 years, the outer planets align in a way that lets a single spacecraft use the gravity of each one as a slingshot toward the next, turning what would normally require several separate missions into one continuous grand tour. NASA had a launch window measured in years to catch that alignment, and Voyager 2 rode it. Even then, an extended mission to the ice giants wasn't a foregone conclusion. It depended on the spacecraft actually surviving in good working order, well past its original design life, and continuing to prove itself capable at Jupiter and Saturn before NASA committed to stretching the mission further outward. Voyager 2 did exactly that, and NASA extended its assignment accordingly, sending it on to Uranus in January 1986, and then to Neptune in August 1989. Target's its own twin, Voyager 1, was never sent to visit at all, having been redirected earlier in its own journey for a dedicated close study of Saturn's moon Titan instead. That's the full weight of what's riding on this one flyby. There is no backup dataset, no second pass, no other spacecraft's measurements to cross-check against. Everything humanity has ever learned about Uranus from a spacecraft's own instruments, its magnetic field, its ring system, its moons, and yes, its unexplained radiation belts, comes from the roughly 6 hours Voyager 2 spent close enough to the planet to gather meaningful data during a single afternoon in the winter of 1986. To understand why this mystery mattered enough to chase for 4 decades, it helps to understand what Voyager 2's Uranus flyby actually was, and how unlikely it is that humanity will ever repeat it anytime soon. Voyager 2 launched in 1977, alongside its twin, Voyager 1, riding a rare planetary alignment that let a single spacecraft use the gravity of each outer planet to slingshot toward the next. After completing its primary mission at Jupiter and Saturn, Voyager 2 was in unexpectedly good condition, prompting NASA to extend its journey onward to Uranus and eventually Neptune, planets its twin was never sent to visit. Voyager 2 reached Uranus in January 1986, and remains, to this day, the only spacecraft that has ever visited it. No orbiter, no follow-up flyby, nothing. Everything humanity directly knows about Uranus from a spacecraft's instruments comes from that single pass. During that flyby, Voyager 2 made a long list of genuine discoveries, transforming Uranus from little more than a blurry telescopic smudge into an actual physically characterized world in the span of a single close encounter that ground-based astronomy had never come close to matching. It found 11 previously unknown moons, bringing the total known at the time considerably higher than what ground-based telescopes had ever managed to detect. It discovered 2 new rings, adding to the faint ring system first detected from Earth less than a decade earlier through a chance stellar occultation. It confirmed the planet's strange near 90-degree axial tilt, meaning Uranus effectively rolls around the Sun on its side rather than spinning upright like most other planets, likely the result of some ancient catastrophic collision billions of years in the planet's past, possibly with another large protoplanet during the solar system's chaotic early formation. And it revealed an oddly lopsided off-center magnetic field, tilted at a steep angle relative to the planet's own rotation axis, and offset from its physical center. a magnetic structure unlike anything seen at any other planet Voyager had visited, and one that remains only partially understood even today. But one particular reading stood out as a problem rather than a triumph. The spacecraft's instruments detected an electron radiation belt around Uranus that was far stronger than anything models predicted it should be able to hold on to. Compared to the radiation environments of other planets, environments researchers had built reasonably solid predictive models around based on each planet's magnetic field strength and general characteristics, Uranus simply had no obvious mechanism that should have let it trap and sustain that much high-energy radiation. Researchers were left with real data, clearly measured by working instruments, that didn't fit the physics they understood at the time, with no easy way to explain the gap. For a long time, this went largely unresolved, in part because nobody had anywhere near enough follow-up data on Uranus specifically to run new comparisons against. Every attempt to model the planet's radiation belts kept running into the same wall, a single, unrepeated measurement, with nothing else from Uranus itself to check it against. What changed wasn't a second mission to Uranus. There hasn't been one, not in nearly 40 years and counting. What changed was that scientists spent the following decades getting extraordinarily good at studying a completely different planet's radiation belts up close, our own. The team that eventually cracked this, led by SWRI's Dr. Robert Allen, took an approach that sounds almost deceptively simple once you hear it described, even though nobody had successfully applied it to this particular puzzle before. Go back to the original 1986 Voyager 2 data and compare it directly against everything researchers have since learned about how Earth's own radiation belts behave, especially during extreme space weather events. Science has come a long way since the Voyager 2 flyby, Allen said, describing the reasoning behind the approach. We decided to take a comparative approach looking at the Voyager 2 data and compare it to Earth observations we've made in the decades since. It's worth appreciating just how much Earth observations actually means in this context. Since 1986, humanity has launched a steady stream of dedicated magnetospheric research missions, specifically built to study our own planet's radiation belts in extraordinary detail, tracking how they swell, shrink, and reorganize themselves in response to different kinds of solar activity, across thousands of individual events, cataloged and cross-referenced over decades. That's an enormous body of comparative data that simply didn't exist yet in 1986, when Voyager 2's own numbers first came back looking inexplicable. Uranus only ever got one data point. Earth, over that same stretch of time, got an entire library. That comparison pointed toward something specific, a phenomenon called a co-rotating interaction region, a particular kind of solar wind disturbance where faster-moving streams of particles from the sun catch up to and slam into slower-moving streams ahead of them, compressing the material between them and generating intense, turbulent conditions as the two streams grind against one another. These regions are well studied at Earth, where they're known to trigger real, measurable space weather effects, distinct from the more sudden, dramatic solar storms most people picture when they think of space weather, but often just as capable of disturbing a planet's magnetic environment. The SWRI team's analysis suggests that a structure like this was likely moving through the Uranian system at the exact time Voyager 2 flew past in 1986, meaning the spacecraft may have arrived in the middle of a genuine, active space weather event, rather than catching Uranus in anything resembling a typical steady-state condition. Here's the part that required the newer Earth data to figure out, and it involves a genuine flip in how scientists understood a particular kind of wave activity. A flip that simply hadn't happened yet back when researchers first tried to make sense of the 1986 numbers. The Voyager 2 data from 1986 showed the strongest high-frequency plasma waves recorded during the spacecraft's entire mission, present right at the moment of the Uranus flyby. Not a subtle background signal, but a clear spike, the most intense reading of its kind Voyager 2 ever recorded across its entire journey through the outer solar system. At the time, the prevailing understanding was that waves like these should scatter energetic electrons out of a planet's radiation belts, knocking them off their stable paths and sending them falling into the planet's atmosphere, where they'd simply be lost, meaning that these waves should have been thinning the radiation belts out, not building them up. Under that older framework, the strong wave signal Voyager 2 recorded should have predicted weaker radiation belts, not the unexpectedly intense ones the spacecraft actually measured, which only deepened the original puzzle rather than explaining it. Since then, research, much of it done using extensive, repeated observations of Earth's own radiation belts across many different storm events, has shown that under certain conditions, the exact same kind of wave can do the opposite. Instead of only scattering electrons away, these waves can also accelerate them, injecting additional energy into a planet's radiation belts and making them measurably stronger rather than weaker, a mechanism confirmed through direct, repeated observation at Earth long after Voyager 2 had already left Uranus behind. SWRI's Dr. Sarah Vines, a co-author on the paper, pointed to a specific, well-documented example of exactly this happening at Earth. In 2019, Earth experienced one of these events, which caused an immense amount of radiation belt electron acceleration If a similar mechanism interacted with the Uranian system, it would explain why Voyager 2 saw all this unexpected additional energy. That's the core of the solution. Voyager 2 didn't necessarily catch Uranus behaving normally with an unusually strong baseline radiation environment. It may have caught Uranus in the middle of an active, energizing space weather event, the planetary equivalent of a geomagnetic storm. With waves that, thanks to decades of subsequent Earth research, scientists now understand can supercharge a radiation belt rather than only draining it. The same signal that once looked like it was pointing toward an explanation for weaker radiation turned out, once reinterpreted through a lens that didn't exist in 1986, to be evidence for exactly the opposite effect. It's worth sitting with just how much this discovery depended on the passage of time itself, because it says something honest about how science actually progresses. In 1986, researchers analyzing the Voyager 2 data simply didn't have the observational history to recognize what they were looking at. The idea that these particular high-frequency waves could accelerate electrons instead of just scattering them away wasn't established yet. It emerged from later research, built on repeated, detailed observations of Earth's own magnetosphere across many different storm events over the following decades, using instruments and monitoring networks that, in most cases, hadn't even been built yet when Voyager 2 flew past Uranus. Without that accumulated body of Earth-based comparison data, there was no way, in 1986, for anyone to look at Uranus's radiation belt numbers and correctly diagnose what had actually happened. The measurement was right there, sitting in the archive, complete and accurate. The framework needed to interpret it correctly simply hadn't been invented yet. In a very real sense, this wasn't a mystery that needed a new mission or a new instrument to solve. It needed 40 years of unrelated research into a completely different planet to accumulate first, so that scientists would eventually have the right framework to look back at old data with new eyes. The answer to a question about Uranus turned out to be sitting, unrecognized in decades of research about Earth, proof that sometimes the missing piece of a planetary mystery isn't out in deep space at all, but right here, in our own backyard, waiting to be connected to the right archived data set by someone willing to make the comparison. This finding does more than close out an old, nagging discrepancy in a data set. It potentially reshapes how confidently scientists can treat anything Voyager 2 measured at Uranus as representative of the planet's normal, everyday state. Humanity has exactly one spacecraft's worth of close-up data on Uranus, gathered during a single flyby that lasted only hours out of a mission that had already spanned nearly a decade by the time it arrived. For 40 years by necessity, that flyby has functioned as the baseline, the reference point every model, every comparison, every textbook description of the planet has had to work from, simply because there was nothing else to compare it against. Every paper written about Uranus's magnetosphere, every prediction made about how the planet's radiation environment should behave, every comparison drawn to Neptune or the other giant planets has ultimately traced back to that same single set of numbers from a single afternoon in January 1986. If the sub-URI team is right that Voyager 2 happened to arrive during a rare active space weather event, that means the baseline humanity has been building Uranus science on for 4 decades might not represent typical conditions at all. It might represent an unusual, temporarily supercharged moment that happened to coincide, by pure chance, with the only few hours humanity has ever spent up close with the planet, the cosmic equivalent of judging an entire city's weather patterns from a single afternoon that happened to be the worst storm in a decade. That's a genuinely significant reframing. It doesn't mean previous research about Uranus was wrong exactly. The measurements themselves were real and accurately recorded, and nothing about this new interpretation calls the raw data itself into question. But it does mean a lot of what's been treated as how Uranus normally behaves may actually be closer to how Uranus behaved during one specific, possibly atypical afternoon in January 1986. Untangling which parts of the Voyager 2 data reflect genuine, stable characteristics of the planet, and which parts reflect a temporary storm passing through at exactly the wrong or right moment, is exactly the kind of question this new research reopens rather than closes. Alan and his team have been explicit about where they think this finding leads, back to Uranus, this time with an actual mission built to answer the questions Voyager 2's single flyby never could. "This is just one more reason to send a mission targeting Uranus," Alan said, framing the radiation belt puzzle not as a solved footnote, but as one more item on a growing list of open questions that a single 1986 flyby was never equipped to fully answer. A dedicated orbiter, something capable of watching Uranus's radiation belts continuously, across many different space weather conditions over months or years, rather than catching one brief, unrepeatable snapshot lasting only hours, could directly test whether the co-rotating interaction region theory holds up, by actually observing how the planet's radiation environment changes as different solar wind conditions sweep past it over time. That's precisely the kind of longitudinal, repeated observation that transformed scientists' understanding of Earth's own radiation belts over the past several decades, and it's exactly what's been missing for Uranus this entire time. There's also a genuinely research-relevant reason to care about this beyond Uranus itself. Allen specifically noted that the findings carry implications for similar systems, such as Neptune's, Uranus's near-twin ice giant, which Voyager 2 also visited briefly in 1989, and about which even less is directly known, given that its own flyby data has received far less dedicated reanalysis over the years than Uranus's has. If a rare solar wind event was capable of supercharging Uranus's radiation belts during Voyager 2's pass, the same kind of event could, in principle, be distorting our understanding of Neptune's magnetosphere too, built as it is on an equally singular, unrepeated flyby 3 years later. A mission architecture built to study one ice giant properly would very likely answer open questions about both. It's part of a broader pattern that's emerged around the ice giants generally in the last year alone. Just months before this radiation belt paper in September 2025, a separate team resolved a different long-standing Uranus mystery, why the planet appeared for decades to give off no internal heat at all, unlike every other giant planet in the solar system, which typically radiate noticeably more energy than they receive from the sun. That puzzle was eventually explained through updated computer modeling, showing the planet actually does emit more energy than it receives, just far more subtly than expected, in a signal that had been effectively masked in earlier analyses. And in August 2025, the James Webb Space Telescope discovered an entirely new moon around Uranus, a tiny object roughly 6 miles wide that Voyager 2's cameras, sweeping past decades earlier, simply never caught, too small and too faint for 1986-era imaging technology to resolve, bringing the planet's confirmed moon count to 29. Uranus, it turns out, has been quietly generating fresh, genuine mysteries and discoveries well into 2025 and 2026, almost 40 years after the only spacecraft that ever visited it flew past and kept going. A steady drumbeat of new findings about a planet still widely and increasingly unfairly regarded as the least interesting stop in the solar system. There's something worth sitting with in the fact that this entire discovery traces back to a single, brief flyby by a spacecraft that's still, right now, transmitting data from somewhere billions of miles past the planet it once visited. Voyager 2 left Uranus behind in January 1986 and never looked back. Literally could not, given its trajectory and its onward assignment to reach Neptune in 1989. It went on to become, along with Voyager 1, one of only 2 human-made objects that have ever crossed into interstellar space, passing beyond the heliopause, the boundary where the sun's influence gives way to the wider galaxy, in November 2018, 6 years after its twin made the same crossing. As of this year, both Voyager spacecraft remain operational, running on a steadily declining power supply from decaying plutonium, with engineers continuing to shut down individual instruments one at a time to keep the rest alive for as long as possible into the 2030s. Voyager 2's low-energy charged particle instrument and its plasma science instrument have both already been powered down in recent years as part of that ongoing effort, leaving a shrinking handful of active instruments still gathering data from the edge of interstellar space. The Uranus data that finally got properly explained this year was collected decades before any of that, back when Voyager 2 was still deep inside the solar system, still years away from its own historic departure into interstellar space, still carrying nearly every instrument it launched with in full working order. It's a reminder of just how much scientific value can sit dormant inside old spacecraft data, waiting not for a new mission, but simply for the rest of science to catch up enough to finally make sense of it. The spacecraft did its job in 1986. It's taken the rest of us 40 years to finish doing ours. To be clear about the state of things, this isn't a case of a wild theory being definitively proven beyond doubt. The SWRI team's explanation is a strong, well-reasoned candidate built on genuine physical mechanisms already observed and confirmed at Earth, but it's not yet been directly verified at Uranus itself, because there's no way to verify it without another spacecraft actually there to check. Allen and his colleagues have said as much themselves. The findings resolve the core puzzle convincingly enough to publish, but they also open new questions about the exact physics and sequence of events that let waves like these transfer energy so efficiently into a radiation belt in the first place. What has changed is the confidence with which scientists can now say they understand why that 1986 measurement looked the way it did. For close to 40 years, the honest scientific answer was a shrug. Now there's a specific testable mechanism, one borrowed entirely from decades of unrelated research into our own planet's magnetosphere, that fits the data convincingly enough to have cleared post-peer review and been published in Geophysical Research Letters this year, under the title Solving the Mystery of the Electron Radiation Belt at Uranus, Leveraging Knowledge of Earth's Radiation Belts in a Re-examination of Voyager 2. Observations, a title that, unusually for a scientific paper, describes almost exactly what happened without needing any further translation for a general audience. It's a genuinely satisfying kind of scientific story, precisely because it isn't dramatic in the way a shocking new discovery headline usually implies. Nothing new was found at Uranus. No new spacecraft flew past it. What actually happened is quieter and, in its own way, more impressive. Old data, patiently re-examined with decades of newly earned understanding, finally gave up an answer that had been sitting right there in the numbers the entire time, waiting for scientists to develop the right framework to read it correctly. It's the scientific equivalent of finally being able to translate a message that was received clearly the whole time, just written, in a language nobody had learned to read yet. There's also something worth appreciating about how unglamorous the actual breakthrough was. No new telescope, no new spacecraft, no dramatic announcement of a mission launch. Just two researchers, a decades-old archive of numbers from a single afternoon in 1986, and a genuinely patient comparative approach that took the extra step of asking what 40 more years of a completely different planet's data might be able to teach them about a question nobody else had managed to close out. That's a meaningfully different kind of story than most of what tends to make headlines about space discoveries, and arguably a more honest picture of how a lot of real scientific progress actually happens. Not through a single dramatic reveal, but through the slow accumulation of comparison data until an old stubborn number finally starts making sense. So the next time someone brings up Uranus's supposedly boring, overlooked reputation among the planets, here's the actual story. The only close-up data humanity has ever collected on it may have captured the planet mid-storm, radiation belts flooded with extra energy by a rare solar event nobody even knew to look for at the time. And it took 40 years and an entirely different planet's worth of research just to recognize what Voyager 2 had actually seen. What do you think? Should Uranus be the next major target for a dedicated NASA mission, ahead of the other outer planets still waiting for a proper visit? Let us know in the comments. And since Voyager 2's old data just rewrote part of what we thought we knew about an entire planet, there's a decent chance more of its archives still have secrets left in them. Stay subscribed, because if another one turns up, we'll be covering exactly what it actually shows.